Assalamu alaikum and a very good morning to everyone. Today we are going to continue our class with the next topic, that is robotic vision. So this is one of the most exciting aspects in the robotic system. Just like us, so our eyes and brain work together to make sense of what we see. So similar to robots, they use cameras and algorithms to see and make decisions based on what they see. By the end of the session, you will understand how robots interpret those images and use them to act accordingly. So let's begin with the history of the digital camera, which is the basic robotic vision. So before we had digital cameras, early scientists like Nips used something called a camera obscura. So think of it like a natural pinhole camera. It projected an upside down image onto a surface. So this basic idea of light forming an image laid the foundation for modern vision sensors used in robotic nowadays. So here is the pictures of basic principles of digital camera that we have today based on this principle. So in a camera, it can precisely measure the orientation of point in space. So when 2D images are captured, they actually contain some information that is valuable to be interpreted as the object in the image. So those photometric information is such as the shape and the color of the object. So then after you have the image, then you can use the computer vision with some algorithms or image processing to interpret the object in the images and to analyze what are the scenes or what are the views that uh, are viewed by the robot in front of the robot. Images in robotics are usually stored in RGB format where you have a three channels of color, that is red, green, and blue. So together, these different colors will form a full color images, as you can see in this left side of the in this left side picture. So from this picture, actually we can access these images as a multi-dimensional arrays. And this multi-dimensional arrays, you just imagine that you have an Excel sheet, but it is in 3D. Usually, the image can be represented by the number of its pixels in Y and X, and also its color data. Okay, for example, like in this case, so this picture can be represented as H times W times 3. So H is the height. So in this from this picture, the height is 512 in Y pixels, and then width is 384 in X pixels. So 3 meaning that this image is using 3D arrays of color, which is consisted of red, green, and blue. Okay, for example, here is some snippet code from a Python programming language. So by using a Python imaging library or PIL, so this code will actually read the size of the image and also print the RGB value of the pointed pixels. Okay, for example, here is the coding to get your image, and then you print the resolution, and then you get the image data, and then you print the image data at this particular pixel point. Okay, so this 383,511 is actually here. Okay, so you get the data here. So the resolution for this image is 512 times 384, which is 512 is the Y pixel and 384 is the X pixels. And then the image data shape is 384,512 in 3. So meaning that 3 is the number of, 3 is the multi-dimensional color that's been used. So in this case, it's using RGB. And at this particular pixel, at this particular point of pixel, so the color here is actually this one. So 76 is the R value, 54 is the green value, and 56 is the blue value. All right. Okay, now we move to the next subtopic, which is the contribution for robotic application. Why do robots need vision? So some of the applications that need vision is the autonomous navigation and mapping. Okay, where you need to have a to detect the obstacle, to detect landmarks from the view of the robot, or maybe in the object detection and recognition. So maybe you have a security robot, so the robot needs to recognize the familiar faces, or maybe with the unrecognized face, that they need to do some security checkup or security measure for that environment. Or maybe the robot is used to track an object, for example, like a speeding car. Okay, and also maybe that robot is going to use gestures or human pose recognition to interact with the human. For example, like when a human, maybe a disability human with hearing disability or speaking disability, so usually they will use a sign language. So maybe the robot can interpret the sign language from the view of the camera vision. And also maybe it is going to be used in the facial and emotional recognition for the social interaction robot, or maybe the augmented and virtual reality implementation. Okay, so for example, like in this figure 6, so a robot manipulator is learning from human using virtual reality. So if using virtual reality, so meaning that the robot needs to interpret the object in front of it by using an image. Okay. So that's why computer vision is one of the important sensor that should be equipped in a modern and advanced robotic system. One of the implementation of having a camera vision is to detect the object and to recognize the object. So imagine you are helping a robot to understand its surrounding, to understand its environment, to understand who are with them or what are with them. So object recognition is, let us say, that's a chair, okay, or that is a person. But do the robot really know that is a chair or that is a person? So it is one of the most critical steps in giving robots awareness is by letting them to recognize, to detect an object and to recognize it from the image. So what is object recognition? So object recognition is a computer vision task that involves identifying and classifying objects within an image or video. So it enables the system to detect and label the object, distinguish it between another objects or another classes. For example, like a car and a person. So it has to differentiate between a car and a person in the image. And then this process is a fundamental in enabling machines to interpret, or enabling the robots to interpret and interact with the visual data to mimic human perception. For example, like we have our own eye, so we have our own brain that will translate those data automatically into a meaningful object. All right. So this awareness of the object recognition will actually create awareness to the robot that allows them to make decisions. So the kind of decision that they need to do is, for example, like whether they need to avoid an obstacle, or maybe they need to fetch the right tools or to fetch the right object, or maybe they need to monitor the correct patients in a hospital. So it is actually like giving them a sixth sense to the robotic system. Okay, that is the objective of the object recognition. So why object recognition is important? Because the robot need to perceive and understand their environment, and so that they can make a decision making. So robot actually can distinguish, to differentiate between the objects, and then between the object and obstacles, and after it detect the obstacles, so it can navigate in that dynamic environments, for example, freely and safely. All right, and then these are some of the applications in robotics that needs object recognition. For example, like the autonomous vehicles. So it needs to detect obstacle. The obstacle can be a car, can be a person, can be a motorcycle. So they need to avoid it during the navigation process, or maybe in the industrial automation where the robot actually can identify and handle parts, or maybe the robotic arm need to do some soldering uh, process where they need to solder in a uh, in a correct contact point, right? And then maybe perform quality checks. They need to do some quality control. They need to detect defect from the object, for example. Okay, in the healthcare, for example, like Da Vinci robot. Okay, so they need to interpret the location or the maybe some of the location of the organ, the path of the vein, for example, right? Okay, and then maybe they need to recognize the medical instruments and then they can pass it to the doctor. Okay, and then also in the service robots and agriculture. So agriculture, for example, like they need to differentiate between the ripe and unripe fruits before they can harvest it. Also, maybe they need to find the location of the fruit before they start to harvest it and so on. So object recognition, it is important because it can actually give a real-time detection and rapid responses to the implementation. And then it also can reduce the false positive during the detection. And it also can be integrated with other systems and technologies, for example, like VR, AR, and others. Here's the process of object recognition. So first, it will capture the image, okay, through a video, through a camera, and then after it capture it, it will extract the meaningful features like shapes and colors to differentiate between the objects in the image, or maybe it will identify the age of the object in the image. And then after it has identified it, it will classify by using AI, for example, okay, to categorize this object, whether it is a cat, or it is a rabbit, or it is a dog, for example. And then after that, it will finally detect where the object is located in the image, like putting a label on it with a bounding box, for example. Okay, so object recognition can come in different type of tasks. Okay, for example, like image classification is basically what is this image about? Okay, it will classifying the entire image into a specific category or specific class. While in the object localization is where is the object? So you have an image here. So where is this cat is located in the object? At which part of the image? Is it in the middle of the image or maybe at the edge of the image? So it is actually identifying the location of an object within an image. That is localization. While on the object detection is actually basically what and where are the objects. So it will identify and also locate multiple objects in that image. And then in segmentation, where you have an instant and semantic segmentation, it's actually a process of painting each object pixel by pixel. So it will classifying each pixels in the image according to its object class or category, which is useful for applications that require precise object boundaries. Okay, this is the task that is available in the object recognition. This is an example image classification by using various methods. So object detection, also known as object localization, semantic segmentation, and instant segmentation. So in the image classification, so it just classified there are three classes in this image, meaning that it has person, sheep, and dog in this image. That is image classification. But then in the object detection, it can object this class. For example, the green box is the person, and then the blue box is the sheep, and the red box is the dog. While in the semantic segmentation, it can actually identify this class by filling up the pixel of that class. Okay, for example, in this case, in the C image, so you can see the person is painted with the blue, light blue, while the sheep is painted with the purple color and the dog is painted with the red color. So actually you cannot differentiate the sheep. Okay, it's all the same shape. For example, like just a car, just a shape. Okay, this is shape, this is car. So it cannot differentiate whether it is a BMW car or whether it is a Mercedes car. Just class it as a car. Okay, so in this case, it just classify everything as a shape. dia tak kenal pun which one is Beda, which one is Ahmad, which one is Ahsen. No, right? But meanwhile, in instant segmentation, it's like knowing the twins, but be able to tell them apart. Okay, for example, the person is because it only has one person, so you just can tell that this is Ahmad. Okay, but for the shape, you have a different shapes, even though it's the same class, but you have a different name of shape. For example, like the red one is Amina, maybe the green one is Abu, okay, the pink one is Ali, and so on. So by using instant segmentation, you actually can differentiate the same the object within the same class. Okay, that is the difference between semantic segmentation and instant segmentation. So this is the detailed explanation between the semantic and instant segmentation when you can read from this table. Okay. So in this slide, it shows the framework diagram that can be used for object detection and recognition. So here is the full pipeline. So image goes in from the image acquisition method, from the images or from the videos, and then it gets cleaned by using the image processing through filtering and enhancements of the image, and then it will detect the features, for example, like the shape or the colors or the gender of the person in that image. And then after that, it will use this feature as a descriptor uh, to match and classify the objects in the image with the data that has been filled up in the database. Okay, and then after that, it will localize the object and draw a bounding box for a different object in that images. All right, and then after that, it will put some labeling to that bounding box or to that object, and then after that, uh, it will be evaluated by using evaluation metrics such as mean average precision, for example. Okay, and then finally, it will building in a reliable robotic vision system by using a real-time processing and optimization. So before we move further into the object recognition, we need to process the raw image first. So it is a critical step in object detection and recognition as it will involve some manipulating and enhancing process of the raw image data to improve the accuracy of subsequent feature that is available, that is useful, can be used as the object recognition task. Okay. So the goal is actually to make the features to be more visible or more distinct and easier to detect from your algorithm. These are the some of the basic image processing that maybe you need. Okay, for example, like pixels and colors models. Maybe you need to change the pixel and color models. You do some filtering or enhancement. You sharp the image. Okay, maybe the image quite blurry, so you have to sharp it. And then maybe you detect the edge of the image because you want to have a distinction object. Maybe the object has a distinct shape, so it's easier for you to recognize it. Where you have some thresholding, okay, you want to convert the image into binary image, so you have to put some thresholding there. Okay, and then maybe some morphological operation, histogram equalization. Maybe you need to resize and cropping the image so that you can save the computation time and so on. But the question now is, do we need all of this? But this one is actually depends on your application. Maybe you don't need everything here. Maybe you need some of the processes here. Each tiny pixels here carry color info. So for this example, in RGB, it a mix of green, red, green, and blue. So the interpretation of this data depends on the color model used. So if you're using the RGB, so you are going to have a 3D array of data. Okay, so each of these tiny pixels, it represents the number of the color that you use here. All right. We have various color models. So the usual use is the RGB and grayscale and maybe HSV. right? So maybe CYMK and maybe lab. So this one is actually depends on your application. So you need to test which color models that suit your application. Not all, okay? Maybe not all images can be evaluated using the RGB, and not all objects in the image can be detected by using HSV. So you have to test it to give you the most distinction value or the most enhanced feature in the image. Okay, so here is the difference interpretation of the image. Okay, so you can see here. So for example, in this figure 13, you can see the difference of the color space between RGB and grayscale. Mhm. And then this is HSV, where it has a hue, value, and saturation, and also the value of the color space here. So it's different. Then we have a filtering enhancement. So blur is to smooth the image, and sharpen is for clarity to enhance the feature. So it's just like applying a makeup or glasses, right? So you can see from here images. So in figure 14, the image before and after Gaussian blur to detect tumor. Okay, so the Gaussian blur here is used to smooth the image. Okay, so from the smoothened image, you can see the feature clearly. Okay, you can find the tumor easily. Okay. So in the edge detection, you are using line to find boundaries between the images. Okay, for example, in the figure 16, so you can see here there are few edge detection technique used in this image. So the grayscale image is the original or the raw data of the image, and then you can see the Sobel. If you're using Sobel algorithm, you can see how the line is detected between the gradient value of the color of the image, okay, and then this is scanning, and then this fluid. So it depends on your application which edge detection technique that you are going to use. So thresholding usually a technique that used to separate light from dark, for example. Okay, maybe to convert image into a binary image. So where the pixels you need to differentiate which pixels will become white and which pixel will become black. So it is useful for object segmentation when the object have distinguishable brightness or color compared to the background. Okay, so it is useful if the color of the background and the image is contrast. So we have two types of thresholding, global thresholding and also adaptive thresholding. So you can see the difference between global and adaptive thresholding in this figure 17. So for global threshold, so you can see it will do all the thresholding in the image in overall. Okay, while adaptive threshold, the value will be calculated for small region in the image, which will allow for better results here. Okay, in case where the lighting is, when the lighting conditions varies on the image. So kalau you guna the global, you can see some of the features of that image cannot be extracted because you use the same thresholding value to all data in the image. But for adaptive, you are dividing the image into smaller region, and then you use a different thresholding for each region. A morphological operation is actually used to clean up the image. For example, like when you capture an image, so maybe it has some gaps, okay, and maybe it has some this one the outliers or the black dots in the images. So you can use this um, this process to fill the gaps or to remove the noise. Okay, just like cleaning the image. So for example, like the erosion, it will remove pixels from the object boundary. Okay, often used to eliminate noise, while dilation is used to add pixels to fill up the image or to fill up the hole or the small gaps within the object. So you can see here, with holes, there are some apa kekurangan to this image. Okay, so this is noise. So by using the morphological operation, you actually can reduce this. Okay. So histogram equalization is used to boost contrast, especially when you play around with the low light images, for example, like the X-ray images. Okay, so you need to enhance the feature in this image. So you play around with its histogram. Okay, so histogram equalization is a process that or technique in image processing that used to improve the contrast of an image by redistributing the intensities of its pixels throughout the image. So this process stretches out the most frequent intensity values, making the image appear more detailed and enhancing features that may have been less noticeable. Okay, maybe some of the feature from the original image you cannot notice it, but after going some histogram equalization, so you can see actually here's some sort of different level of boundary here. Okay, so this one can be achieved by using the histogram equalization. So in the image resizing and cropping, is actually resizing is for consistency. Maybe you have 1,000 of images, so you want to have a consistent image size, so you resize every of each of the images. For example, like 300 times to 300 pixels only. So you are going to have a consistent image size for your processing. Okay, and then cropping is actually to focus only on what matters. Okay, for example, like maybe you want to find the region of interest, you already find the ROI, so you just crop at this ROI area only. That is resizing and cropping. Okay, after we have do some correction or after we have improved the image through the image processing technique, then after that we need to extract the feature that is available on the image. So features is actually parts of the image that are unique, that are distinguished between one object to another, that has some noticeable distinction between one object and another. Okay, so it can be a corner, it can be a point, it can be edges, it can be texture, it can be shapes. So this act like the object's fingerprint, like a unique ID to the object. So here are the common feature detection and extraction algorithm used. For example, like the Harris corner detector, SIFT, SURF, or RB and others. Okay, so here are the example, the SIFT feature extraction algorithm that process this woman image. Okay, it will find the extraction, it will find the features, and then it will extract the features by using the SIFT algorithm. So this feature is filled up in this table or in this pixels array. Okay, and then this is going to be the unique ID of this woman. And see, this is the normal way of feature detection and extraction process. So it has 5 basic steps. The first one, you have to pre-process the image. Okay, and then you have to detect the feature, and then you have to describe the feature, and then you have to match the feature with the image in the database, and then you have to do the post-processing. Okay, meaning that you have to refine the matches. For example, like if let's say the feature matching here does not achieve 80% of accuracy, so you have to look back into the feature detection and feature description, or maybe in the pre-processing. Okay, you have to redo some of the algorithm. You have to try some. You have to tweak some of the parameters of threshold in one of these steps, and then you have to do the matching again, and then you have to evaluate it by using matrices. Okay, once we have extracted the features, we match them to known ones. Okay, meaning that you already have one known data in the database. So like facial recognition, so we compare features to a database and then we classify the object accordingly. For example, like I have my own face, okay, and then I extract the feature from my face and then I keep this one in the database. And then I will take another picture of me and then I need to detect any features that are available in this new image. And then once I got the feature, then I have to compare this feature with the feature that is available in my database to classify or to match whether that is the same person. That is, for example. Okay, and then to know whether this person is the real person, you have to look into the score, matching score. Okay, for usually kita akan take the matching score ni between 95 to 100 or maybe 99%. So 99% from this matching process telling you that that is really me, not the other person. Okay, that's why we have a score here to see whether the classifier computes for each candidate correctly or not. Okay, some of the application we just don't want to know what something is or maybe what are in the pictures, but sometimes we want to know where it is in that picture. Okay, that's why we need to do some object localization and bounding box. So bounding box helps us draw a rectangle around the detected objects, providing special context. So the special context is the size of the image, for example. Yeah. So there are actually the key components in object detection that help identify not only what an object is, but also where it is located within the image. So localization provides partial information, allowing system to draw bounding boxes around detected objects to highlight their position. For example, like in this figure 23, in the left picture is the difference between classification and localization. Okay, while in the right picture is the properties of the bounding box. Okay, so here is the classification. Okay, you can classify there is a cat in that picture, but where is the cat is located in the image? So you are using bounding box. Okay, you are using bounding box to locate the cat in that picture. Okay, so this bounding box will give you the special information, for example, like the width and the height, and then the location in the XY coordinates. That is localization and bounding box. Instead of detection and bounding box, we also have a similar things, classification and labeling. So, for example, in this figure, so the the object has been detected and also being labeled. For example, like this one, this is a private car, okay, private car, and this is a bus, right? So it can differentiate and label it, right? So there are two types of labeling. First, by using text and also by using pixel-wise labels. So pixel-wise labels meaning that you label the object by using a different color on that pixels. So how do we know our system works well? So we need to do some evaluation metrics. So metrics like IOU, precision, recall, and MEK help us evaluate the accuracy of detection and classification. It's like grading the robot's eyesight, okay? Just like grading your eyesight at the optometrist, for example. We have the intersection over union, which is IOU that I've just pronounced just now. So it will measure the overlap between the predicted bounding box and the ground truth bounding box. It is calculated as the ratio of the area of the overlap to the area of union between these two boxes. Okay, so this is the formula. Area of overlap is divided by the area of union. So you will get the range between 0 to 1. So where 1 indicates a perfect overlap between the predicted and ground truth boxes, meaning that you are actually detecting the correct image in the correct location. And 0 indicates no overlap, so meaning that you are not detecting the correct object. So this is intersection over union. You can measure the precision of your detection by using this calculation where, for example, in this scenario, your model detected 100 of objects, but only 80 of them are actual objects, meaning that it is true positive detection, while 20 are incorrect detection or false positive. So you have the true positive, which is 80, and then you divide with the true positive plus with the false positive. So you get the precision of 0.8. So it means that 80% of the detected objects are correctly identified. So it indicates that a relatively low rate of false positive. So meaning that your system is okay, because you detected 80% from the detection is correct. Okay, so it is reasonable and a reliable processor system lah, yeah. Let's say you receive, so if let's say you receive a lower precision value, for example, like 0.6, So meaning that you have to look back into your feature selection, whether you actually extract the correct features, okay, and then maybe you need to look back into your data training, and then you have to look back into your data input, okay. So usually we will accept the system is detecting the object correctly by looking at this precision percentage. Another evaluation that we can use is recall. So let's say you have 120 objects in the ground truth. So your model can detect 100 correctly, and 80 of your model can detect 100 of objects, and then 80 of them are correct. So meaning that true positive, it detects the object correctly. So false negative here are 40. So it means that the actual objects, um, the model failed to detect. Okay, so you use this recall calculation, true positive divided by true positive plus false negative, so you will get 0.67. So it means that the model detected 60% of the actual objects, indicating a moderate rate of missed objects. So another 40 object to the miss, right? So this is the recall. So either you can use the precision or either you can use recall. Since we have a precision and recall, so both of these value can be used. They can be correlate, and then the correlation will become the average precision. So the average precision is actually building a graph with the with the y-axis of precision and the x-axis of recall. Okay, and then this average precision value is calculated um, the area under the graph, okay, where the approximate the PR curve with rectangles and interpolation, and this is the interpolation of 11 point of average. So meaning that you have 11 point of data, and then you will see the average precision, which is the area under this graph. It will become the average precision of this um, object detection. Okay. Right. Another method of calculating this average precision graph is by summing the areas of these rectangles. You develop a rectangle here, okay, and then you calculate this rectangle for each region, and then you add it or sum it. So this is another way of calculating the AP value. So this is the example of how to calculate this AP value by using the rectangle area here. You have 11 points of data, and then you're going to find the area of the rectangle for each point, and then you sum it. Okay. If your system has more than one class, okay, you have a multi-classes, so you can use the mean average precision. So AP value, it can be calculated for each class, just like the previous example. So the mean average precision can be calculated by taking the average of AP across all the classes under consideration. Okay, if you have three classes, so you need to find the AP for each class, and then use this mean average precision for the overall precision for overall classes. So now let's go beyond still images that we discussed just now. So object tracking follows the object as it moves frame by frame. So imagine playing hide and seek. So the robot has to keep eyes on the object continuously. So that is object tracking. It will track the object from one frame to another frame. So what is object tracking? So object tracking is a process of following a specific object or multiple objects across a sequence of frames. Okay, for example, like in this figure, so multiple object tracking within a few frames. Okay, so it tracks and then it labels each object. So meaning that it is following a different objects in every frame. Okay, it can differentiate between different classes or objects in the frames. So what is the difference between object localization and object tracking? So object localization, it will locate the object in the image. Okay, while object tracking, it will track the object in a multi frames of images. Okay. So these are the key challenges in object tracking. So where you're going to have an occlusion. So objects can be fully or partially blocked by other objects. So making it difficult to track. Maybe the illumination changes, varying the light between one frame to another. Okay, because the camera is moving. So maybe some of the frames has a very light conditions. Maybe some of the frame are very have a dark conditions. So it will complicate the tracking. And then scale and orientation variations. Okay, object may change the size. It's the same object, but it may change the size or rotate. Okay, making that you have to have a robust tracking method to track this kind of object. Okay, and then maybe the clutter behind the background. So you have a very complex background, so you have to distinguish between that background and your object, and then you have to track the object in that cluttered environment. So these are the key challenges in object tracking. And then we have a single object tracking, and then we also have a multi-object tracking. So you can, for a multi-object tracking, you need to assign some unique ID, okay, for each object. But for single object tracking, you don't have to assign any ID, okay, because you just track just one object in that frame. So these are some of the object tracking algorithms. So we have two types of algorithm, the traditional and also the modern. So basically the modern is using AI, okay, while the traditional object tracking algorithms is using mathematical function, right, or maybe a filter. Okay, kalau in the modern object tracking, usually using a neural network. So this is the example of using the Siamese network to detect the object or to track the object. Okay, so you can look at this example. Okay, now let us look into a real application, which is the line following robot, where it has to track the line because you are going to use this application in your mini project later. So a line following robot uses a vision sensor and OpenCV to find and follow a black line. Okay, and then after you have detect and follow after you have detect the black line, then you have to follow it by using a certain controller, for example, like a PID controller, to adjust the wheel's velocity and so that the robot will stay centered or in the middle of the line. Okay, just like a self-driving car staying in its lane, just like you drive a car and you stay in your own lane. Yeah, that is the analogy of having this autonomous line following robot. These are the example of finding the contour line in the line detection by using the OpenCV. Okay, you have the input image acquisition here, and then you have the image processing here. Okay, and then you have a feature, and then you have a detection here. Right, so this is basically the basic process of detecting the line from the image that you are maybe later on you are going to implement by using this kind of process. So this is the detail of the region of interest from the image, where this is your black line here. So from the black line, you need to find the centroid of your black line, and then you have to compare with the frame centroid. So this error, you can use this error to determine the control of your robot. So for example, you're using PID, so whether from this error, you need to increase the right wheel or you need to decrease the left wheel, okay, because your objective is to make sure that your robot stays centered or in the middle of the line to follow this line. So you can use this as a error between the contour centroid and also the frame centroid. Okay, so this is how you determine the contour centroid from one frame to another. Okay, and then from this error, you need to calculate the right speed and left speed by using the PID controller. So that wraps up for robotic vision. So from pixels to object tracking, you now understand how robots see and make sense of the world. So next time, we'll go deeper into the implementation, especially in the line following robot by using the image and detecting the line from the image. Then until then, we'll see you again in the next class. Assalamualaikum.